In this lecture, I'm going to move ahead and we are going to work with deep neural networks, and these are the data, the iris data set. You can see the data here. I'm going to import the data iris pt.read_csv, iris.csv, and these are the data. So we have the 3 different species, and they are categorized on basis of 4 quantitative predictor variables, and we have 150 rows and 6 columns. So this is what iris.shape tells us, the rows and columns. Now I don't need the ID column, it's really not useful for me. So the first thing we can do is to remove the ID column. Iris.drop ID, so this is the column name. I want to drop this. Axis is equal to 1, so we are going to drop the column like so. In place true, so we specify in place true, especially when we are removing just one column. And we can see how many data points do we have for each class. So for that, print iris species dot value underscore counts, and as you can see, each species, it has 50 observations, and these are things that I'd covered earlier on. So this is a basic cleanup that we give to our data set. Now we are going to implement our machine learning model. From sklearn.model_selection import train test split. From sklearn.metrics import confusion metrics accuracy score, which will let us evaluate how good or bad our model is. So X, this is here is where we store the predictors. So iris.ilog 0 is to 4. So basically we are going to keep the first 4 columns 0, 1, 2, 3, because when we say 4 it won't go up to 4, as predictors, and the final, the 4th column, and which is going to be the species, because here the count begins from 0, is going to be the response variable iris.ilog, 4 response variable. Now the first thing, as we did in the previous lecture, is to convert the categories to numbers. So we can do it the way I did it back then, or for I in range length y, if I is iris setosa, we set it to 0, iris versicolor to 1, and then what is left over, virginica, will be 2. So basically there are different ways of converting categories into numerical representations, and this is the second way of doing that. So now we are going to normalize the X so that our gradient steps converge faster. So even when you work with artificial neural networks or deep neural networks, it's a good idea to try and normalize your predictors. So from sklearn.preprocessing import normalize. So X normalize X, and what it does is basically it implements this formula. From each value of the predictor, it is going to subtract the average of that predictor and divide it by the standard deviation, and that's how normalization works. Y np.array, y as type int, because 0, 1, 2, they're all integers, and that's what we do. Now we are going to split our data, our training, the entire data set into training and testing data. X underscore train, X underscore test, Y underscore train, Y underscore test. I'm going to call the function train test split, pass in X and Y. X contain the predictors, Y the response variable. The test size is 0.1, which means that I want to have 10% of the data for testing and 90% for training, and I specify random state 1, which ensures that I end up selecting the same testing sample each time, and this is how things are. Now from torch import optim, import torch NN as NN, and this is where basically the magic happens. And now we are going to, because with deep neural networks we need to have 2 or more hidden layers, and with artificial neural networks we just have 1. So now we are going to have a very simple deep neural network with 2 hidden layers and 1 output layer. So the architecture is going to, the input layer is going to comprise of 4 neurons because we have 4 inputs. The first hidden layer will have 27 neurons, and you can decide on any number you like. We can easily make it 25. The second hidden layer will have 9 neurons. And the output layer is going to comprise of 3 neurons because it's 3 classes that we have. So it's 3 categories that we are trying to classify. And then we are going to use, for evaluating the loss during backpropagation, we'll use the negative log likelihood loss, and it is useful to train a classification problem with a number of classes. And we are going to use SGD for gradient descent optimization to update the weights. So basically this is how we are going to work. Model, I'm going to create a variable model, nn.sequential. So nn comes from here because this is how I'm going to define my neural network. nn.linear for 27 because we have 4 predictors and 27 neurons in the first hidden layer. Pass it to the activation function ReLU. You already know what activation functions are. nn.ReLU, nn.linear. Again, these are the hidden layers. Neurons in each of the hidden layers. 27 for the first hidden layer, 9 for the second one. Again, pass it into the activation function ReLU, nn.linear, 9, 3, and we have 3 output classes. nn.log softmax, dimension 1, and this is the criterion for evaluating the loss. nn n triple L loss, and the optimizer optim.sgd, the model parameters, and a learning rate of 0.03. You can even change it to 0.01. And this is what our model looks like. We are going to define a predict function in which we are going to feed in the model and the inputs, and that's going to predict an output for us. Output model inputs, return output data .numpy argmax axis 1. And then we are going to make torch tensors, base data, and use those for dating, for training, like so. X underscore train, torch from numpy, you've already seen that. X underscore train dot float. These are going to be float variables because these are the predictors. The same for test. So we converted them to numpy, and now we are going to convert it to torch by saying torch from numpy float. Y underscore train, and this, because this is a response variable, we are going to retain that as dot long. Epochs 1000, batch size 15, number of batches 9. And this is for, we create lists for costs and test accuracies. For E in range epochs, so for 1000 epochs, running loss 100. For J in range number of batches, and we have 9 batches, so we are going to iterate over 9 batches. X batch, X train, batch size, and basically we are going to take a batch of data for training and take only 15 entries, and that's what batch size does in each run. In Pytorch, we need to set the gradients to 0 before starting, and that's what I did in the previous lecture. Optimizer.0 underscore grad, output model X batch, and this is where we do the forward propagation. Loss criterion, which is the, again, I define the criterion here using the log negative log likelihood loss. So now that is something we are going to use for calculating the loss criterion. Output, compare it with Y batch, the response variable batch, loss.backward, performing backward propagation. Optimizer.step, this is where we update the weights, running loss, and find the loss during this step. So again, we are going to create a variable ypred, predict, model X underscore test. So we are going to implement the model that we created on the testing data set, and for accuracy we are going to compare the average of the testing response variable with the predicted response variable, and we can print the accuracies, cost.append running loss, and test.accuracies append accuracy. So again, we can see, and in the first couple of epochs, our cost is high and the accuracy is low. And we continue. So by the time we cross 200 epochs, the accuracy has gone up 0.6. At 0.8, 7. And then finally, by the time we cross 700, we get an accuracy of 1. So basically, this is how and that's why we use so many epochs, because with every epoch, the accuracy goes up. And we can see the training costs, and the training costs start coming down. And the test accuracies, this is how they increased. So after 800 epochs, we cross the accuracy. We get an accuracy greater than 0.9. And now we are going to predict ypred is the predicted response variable predicted on the testing predictors, and the accuracy score is 1. It's unlikely that you'll get 100% accuracy on your testing data set, but it just goes to show how powerful deep neural networks can be.